This is an example problem that we did in class. P of x is equal to 2x to the fourth minus x to the third minus 2x squared plus 13x minus 6. And the first thing we want to look at is it's a fourth degree polynomial. So the fourth degree means that we're going to have 4 complex zeros. Now remember, they don't have to be imaginary. They could all be 4 real zeros. So we could have 4 real zeros. We could have 2 real zeros and 2 complex. That means imaginary. So I'll put down imaginary. Or we could have no real zeros and 4 imaginary. So there's a lot of different options there. Remember that our imaginary numbers always come in pairs. So i's come in pairs. I's come in pairs. And they have to, so there's got to be 2 of them, which is why when we have 2 real zeros, we can only have 2 real zeros. We can't have 3. It wouldn't make sense to have 3 real zeros and 1 complex because my i's have to be in pairs. Okay, so that's the first thing we need to look at. The second thing I'm going to look at is the fact that this is a fourth degree. That means it's an even an even power. So an even power means that my end behavior, since it's a positive even power, my end behavior is going to be both up at the end. Just some very interesting things that we should know about our graph. Next thing I'm going to look at is Descartes' rule of signs. And Descartes' rule of signs says that I'm going to look at P of x and look at the number of changes in signs. So remember that this first term is going to be a positive. Since there's nothing there, it's assumed. So we have 1 change in sign, doesn't change, 2 changes in sign, 3 changes in sign. So we're going to have 3 or 1 positive real 0. And remember, it goes down by 2's because 2 of them might be imaginary. So we're going to either have 3 positive real zeros or we'll have 1 positive real 0 and 2 of them will be imaginary. Next I'm going to figure out what P of negative x is and look at the change in signs for P of negative x. So I'm going to put in a negative x wherever I have an x in my original function. And when I do that, I end up with 2x to the fourth plus x to the third minus 2x squared minus 13x minus 6. So in this particular problem, I have 1 change in sign. So that means I'm going to have 1 negative real 0. All right, the next thing I'm going to look at is my rational zeros theorem. So the rational zeros theorem says that I'm going to take my p over q, and p is my constant term, and q is my leading coefficient. And I'm going to look at their factors. So I'm going to look at the constant term factors, and I'm going to divide it by the leading term factors. And we want to include both the positive and the negatives. So p in my original function is 6. So I'm going to be looking at factors of 6 and dividing it by factors of 2. So factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. I'm going to divide that by my factors of 2. Then I'm going to take each one of my factors of 6 and divide it by my factors of 2. So I end up with plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 3, plus or minus 3/2, plus or minus 6. Now notice that you never repeat any of your possible rational zeros more than once. So now looking at all the information that I have in front of me, I know that I'm going to have a possibility of 3 or 1 positive real 0. So I should have at least 1. And I'm going to have 1 negative real 0. So I can either start on the positive or the negative side. And I'm just going to pick the positive because that seems to be easier for me. And I'm going to start off with my integers because those are easiest to use synthetic division on. So I'm going to take 1 and I'm going to synthetically divide it into my original function, which I'm writing down now here. And I'm going to come up with 6 as my remainder. So that means P of 1, using my remainder theorem, is equal to 6. If I look back at my original function and I put in a 0 wherever I have an x in my original function, so if I put in a 0 for all the x's that I have in my original function, these first 4 terms would cancel out and I'd be left over with just negative 6. So the reason I'm looking at that is because I know then that p of 0 is equal to negative 6. Why is that important? Well, if we were to graph these, and I'm just going to do a real quick sketch for you. So p of 0 is negative 6, and we're just going to make each of these equal to 2. So negative 6, 0, negative 6, we're down here. And I'm looking at p of 1, that means that we're going to be up here. So to get from p of 0, from when x is equal to 0 to x is equal to 1, I'm going to need to go up like this. And here is x equal to 0, and here is x equal to 1. So to get from 0 to 1, I needed to do what? I needed to go across the x-axis. And when I cross the x-axis, this is a possible real 0. Well, it actually is a 0. So that means that between x equal to 0 and x equal to 1, I have a 0. So I'm going to look back at my possibilities, and do I have any numbers that are between 0 and 1? Any positive numbers between 0 and 1? 1/2. So I'm going to try 1/2. So now I'm going to synthetically divide using 1/2 as my 0, and going back to my original function and synthetically dividing, and I found a 0. So I know now that x equal to 1/2 is a 0 of my function. So now I can either continue in a positive direction, looking for zeros, because I have a possibility of having 3 of them, or I can look in the negative direction. Well, remember, there's only a possibility of having 2 more positive real zeros. There's also a possibility that I have 2 imaginary zeros. So what we did during class, and which I agree with, is we're going to go look for the negative zeros, because there is a negative 0. And when I go to look for the negative 0, I'm going to use my reduced polynomial. So I'm going to be using this polynomial, which is 2x to the third plus 0x squared minus 2x plus 12. So that's the polynomial I'm going to be using now to look for my negative zeros. Okay, so using this polynomial, I'm going to start looking for my negative zeros, and the first negative 0 I'm going to try is negative 1. So using 2, 0, negative 2, 12 is my top line. Remember, you need to put a placeholder in for x squared. And doing the synthetic division, I come up with 12. So that means that p of negative 1 is equal to 12. And I'm going to go back and look at my function that I'm using right now, which is my reduced polynomial. And that tells me that p of 0 was equal to 12. So I really haven't gone anywhere, have I? So negative 1 doesn't work. I'm going to go to my next negative 0. And again, I'm using my integers rather than my fractions. Just easier to deal with. And I'm going to try negative 2. So I'm going to bring down 2, and then works. So that means that p of negative 2 is a 0. So that means that x equals negative 2. So I've now found 2 zeros. The reason I used my reduced polynomial was so that when I got done doing my synthetic division, I am now down to a second degree polynomial. So this becomes 2x squared minus 4x plus 6. And now, if it's a second degree polynomial, I can either factor or I can use the quadratic formula. You always want to try to factor if you can. It's a little bit faster than the quadratic formula. First thing I'm going to look at is a GCF. I have a GCF of 2, so I'm going to factor out 2, and I end up with x squared minus 2x plus 3 equals 0. Now when you factor out this 2, I could have easily just as divided everything by 2. So if I divide the left side and the right side by 2, these guys cancel out. This ends up being 0. So now I'm dealing with the polynomial function x squared minus 2x plus 3 equal to 0. To factor, I would need to find factors of 3 that give me a sum of 2. Factors of 3 are 1 and 3. They're not going to add up to 2. So I know I need to use the quadratic formula, which is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And remember that a is the coefficient of your first term, your lead coefficient, which is 1. b is going to be negative 2. And c is going to be 3. Now, you had a student in class asked about the fact, why are we using the reduced polynomial? Why didn't we use the original polynomial in our quadratic formula? We could have. It just makes it for bigger numbers and makes it harder for us to reduce when we get down to the bottom. So you always want to factor out GCFs if you possibly can. So I'm going to go ahead and put in the values that I have here. So I'm going to have the opposite of negative 2, which is a positive 2. I'm going to have negative 2 squared minus 4 times a times c. And then make sure that you divide the entire thing by 2a, which is 2 times 1. Simplifying. 2 plus or minus the square root of 4 minus 12 all over 2, which gives me 2 plus or minus the square root of negative 8 all over 2. So when I end up with a negative 8, I know that I'm talking about a complex zero. I need to make sure that I put in an I. So I'm going to rewrite this as 2 plus or minus the square root of negative 1 times the square root of 8 all over 2. The square root of negative 1, I get I. And the square root of 8, I can simplify to 2 square root of 2 all over 2. Then I'm going to make sure that I divide each one of my numerators by 2. So doing that gives me 2 over 2 plus or minus 2 square root of 2 over 2 I. And then finally, simplifying one more time, I end up with 1 plus or minus the square root of 2 I. So my zeros then end up being x equals 1 plus the square root of 2i, x equals 1 minus the square root of 2i, x equals 1/2, x equals negative 2. So if you think back to what our original problem was, and Descartes' rule of sign, it said we would have a possibility of 1 positive real zero or 3. Well, we ended up with 1, and we're going to have 1 negative 0, which we did end up with. And then we ended up with 2 imaginary zeros. And remember, these have i's in them, so therefore they have to be in pairs, and the pairs have to be conjugates of them, which they are.